Typically, yes. Yeah.
Okay. Okay. Hmm.
Depends, of course, on the
Sorry.
parameter. If the parameters are infinitesimally small, you would
Hmm.
be in that immediate neighborhood. But the whole
Okay.
point
Makes.
of this thing is because you can have one parameter subspaces always, you can use them to go to other places as well. And the whole reason why the theory ultimately ends up being a lot simpler than it in general would have been is that every region is sort of similar to the identity. That is, because you can go from identity to other places by doing this kind of transformation, you at every point you essentially have a replica of whatever is happening near the identity. So the tangent plane of the identity is sort of typical. It's the same behavior can be found everywhere.
Okay. Sir, I had another question from the
Yeah. Right?
previous class that it's regarding the how we found out the character tables for the permutation groups.
Mm-hmm.
So in that case, we did it for S5. So in case of S5, we used the fact that we know the identity permutation and the alternating permutation,
Yeah.
and then used the character table of S4. So
Right.
what this so it I think it worked because from S4 to S5 the number of character increase is 2. It was 5 in S4 and number of
Yeah.
characters in
Right. So if you go to the
uh,
next step, the increase will be bigger. If that's what you're
yes,
worrying about, right?
yes.
In
So
fact, what will happen is if you went from S5 to S6, all the three you are going to get are going to be all the three new characters, compound characters you're going to get are actually going to be independent of the previous ones. That is the ones you already know. Okay.
hmm,
Right now, what has
hmm,
happened is whatever new compound character you have got,
hmm,
they actually you could find that they have two adepts in them, and one of them was already the one which you have already written down. That is
hmm,
that you already have. Now, by the way, of course, once you get a new character, say, suppose you start with only two, right? The identity and the alternating. Okay.
yes.
Next, when you have a single compound character in which either the identity or the alternating is in there, you can take it out. You would actually end up with another simple character, right?
Hmm,
Another character from an adep. So next
hmm,
time when you're working with it, you can actually use that again. Use that too to figure out whether it's also in there. However, it will soon happen that you will end up with new compound characters in which none of the ones which you have already found out are already there, have already been found. Okay?
okay.
I guess that's the problem you're driving at because so
Hmm,
far our method has worked simply because whatever new compound character you have found, you
it was
already
already
had a compound had simple characters in them which you knew and you could take them away and you would end up with new simple characters,
yes.
right?
Hmm,
Now
Oh,
it yeah.
actually, for S5, the Chi5, Chi6, Chi7,
Okay, I've got.
I mean the new characters,
Mhm.
they come from the like the unknown
Okay,
ones
so
only.
maybe for S5 it does.
He's talking about like
I've
beyond.
forgotten where it happens, but anyway, somewhere down the line that's bound to happen. Okay, maybe okay S3 to S4 we did right. That was sort of got a new compound character where you had previous things already. But I'm not sure whether I don't remember
Yes.
exactly whether it happens from between S4 to S5 or S5 to S6 or wherever. But somewhere down the line is bound to happen that you will end up with new compound characters which cannot be expressed in terms of the old ones you already know. Maybe it happens as you were saying for S5 itself. Okay, so S5, okay, S5 has seven, yeah, seven adepts, seven because of seven classes, and you already could. Okay, so you will be able to find some of them, I guess, by using the previously known characters. But after that, you will find at least a few which cannot be written down in terms of any of the characters you know. So let's just say I'm not sure whether it happens for S5 because I don't remember this. You could always work that out, but that would take too long. So for S5, let's just say for S5, you may end up with the last three characters coming out to be compound characters which are not things you can write in terms of the previous ones. Okay, and they're also different. You know that there are 7 irreps, so these have to be made out of some of the 7 irreps, and you can also figure out that they are made out of 2 irreps each. That's again by using the sigma m alpha square, right? That's a, if you use a reducibility criterion, it not only tells you whether it's irreducible, it also tells you what sigma m alpha square is, right? And if you know sigma m alpha square from, if it, say sigma m alpha square comes out with 2, then you know it has to be 1 each of 2 irreps. Okay.
Hmm.
So if you have that, you can write one of them as chi5 plus chi6. Let's say. I don't know what chi5 and chi6 are yet, but you can write them as chi5 plus chi6. Okay. The next one would again turn out to be a sum of 2 irreps, and they can't be the same 2 irreps because then you would have ended up with the same compound character. So just call that chi6 plus chi7. You can do that, right? You can just say chi6 is the common character between them because there are only 3 left. You can't have 4 independent. So one will be chi5 plus chi6. Next one will be chi6 plus chi7. And the third one, which is different from the other two, will have to be chi5 plus chi7. Okay?
Yes, sir. All these processes are fine when the increase is by 2.
Yeah, that is precisely why that method is not the method that is used for larger groups. Why do you think we talked about the other version? The one when you talked about, so basically what we said was n can be partitioned, right, into a partition lambda, and then we say g lambda 1
Sir,
has,
I think if you're writing on the screen, we can't see anything. Your presentation is not on, I think.
so it was on, I forgot to restart it again. Okay, entire screen. Uh, yeah, now it's should be back. Remember, this is what we said. We said that this is a subgroup. Okay, these are not G's, these are actually S's, but anyway, just S lambda 1, S lambda 2, S lambda 3, if you take the inner product, and that's how we figured out that alpha factorial by alpha 1 factorial, alpha 2 factorial, alpha n factorial sum over all alpha is such that sigma alpha is equal to alpha, sigma beta is equal to beta, and so on, with the well, alpha 1 plus 2 beta 1, etc. equal to lambda 1. These conditions all thrown in. These were compound characters. This was a different approach. This was not what we did before. Because earlier what we did was we started with S2, then we went to S3, then with S3, from S3 we went to S4, then we went to S5, and so on. So, of course, the other problem with this method is, suppose I want S20. Even if you discount the difficulty that you're talking about, that at every stage the thing becomes more and more complicated. If you want S20, you have to start with S19, but then you have to go to S18, S17, all the way down to S2, S3, S4, which you know, and then get to that. Right? This works for small and okay, but for large and this is not technical, not feasible. So this is the other approach, where we said that Sn always has subgroups like this, and you have one such subgroup for every partition of n. Okay, so that's a bit promising because that will give you one compound character for each irrep, and those compound characters can be found out directly by using the identity representation for the subgroup and just counting how many times every class element, or how many class elements are there which are also in the subgroup. Right? You remember that's the formula that we had, right? Mod G by mod H times number of elements in a class C, and this is number of elements of the class C which belong to H. This was a compound character for the class C. And this is something you could easily figure out by using simple combinatorics. Okay, what I did not finish here, I did not finish this at all. And I said this is something which one of you can take up as part of your final presentation, which is starting from this, you can express these coefficients, which are multinomial coefficients, and just build on whatever you knew from class 12 algebra to show that these can be read off as coefficients of certain polynomials. Okay, just like in binomial theorem, you have these combinations. You can do it with multinomials as well. And using that, what you could show, sorry, let me just open the door. Okay, using that, what you could show is that these compound characters actually happen to be independent of each other. So there's no, so you get exactly as many compound characters here as the number of adepts. And you can show that these compound characters have just as much information needed to find out each of the characters for adepts. And that is how you end up with the final formula for the characters, which essentially comes from by using the Young tableaus. This is basically the route to Young tableaus. I didn't finish that simply because I didn't have time. But
Okay,
any one
sir.
of you who are interested, you should be able to read up this process. This is basically Frobenius's original process, which gives rise to the Young tableau method for representing SN adepts. And from here, with a small modification, you can go to finding adepts of SUN as well and classifying adepts of SUN using Young tableaus. So, in most textbooks, at least physics textbooks, you will find standard rules which tell you how to calculate the characters from the tableaus. I'm trying to give you a picture of where the rules come from. I don't have the time to complete the proof of this, but once you see the proofs, things like hook laws or things of that kind, which you will find in plenty of textbooks. In almost all textbooks, the rules are given, and the rules are pretty easy to use. Okay, but where the rules come from is basically arguments like this. Is that satisfactory? I simply don't have the time to go through the whole thing. That's why I'm just indicating how these things are arrived at. So, as you correctly said, the approach that we talked about at the beginning is something which is impractical for large n's. But this approach actually works for any given n. It doesn't really rely on the earlier Sn values being characterized. And it so happens that although the details are rather long and tedious, at the end of the day, you end up with a rather simple bunch of formulas. For example, if you want to find the dimension of an adept corresponding to a particular cycle structure, what you would do is draw the Young tableaus and then use a hook formula. Remember what the hook formula is, right? You take this, find out how many cells you're crossing for each hook, assign numbers for them, multiply the number of the hook numbers and divide n factorial by that. That gives the dimension of that particular adept, which is represented by a tableau. Okay. It so happens, as we said earlier, that for every group, the number of classes and the number of adepts are one and the same. So there is a one-to-one correspondence between classes and adepts, right, for every group. But that one-to-one correspondence is not really natural. All you are saying is because there are same number of elements in the two collections, there is the collection of classes and the collection of adepts, there has to be a one-to-one representative correspondence. But there's no reason why this particular adept has to go with this class. With Sn, things are different. With Sn, you can, using the Young tableaus, you can construct a very definite correspondence between classes on one hand, which, by the way, if you remember, where does this class tableau collection come from? A class is characterized by the number of different kinds of cycles it has. And that gives rise to a partitioning. And this partitioning is basically what you are seeing here in the form of a tableau. And on the other hand, tableaus are directly connected also to adepts. And you can lay down a one-to-one correspondence between classes and adepts, which is sort of natural, which is not artificially imposed just because that their numbers are the same. Okay. So anyway, I will have to leave this topic and go on to what I wanted to talk about today because again, sorry, I don't have much time really. Any further questions about this? Although, frankly, I'm not in a position to take too much time over this.
No, sir. It's okay.
Okay, so let's quickly go over what I wanted to talk about today. And once again, I'm really going to jump through a few steps simply because, again, lack of time is a good excuse to have at any given stage. What we saw was that if you have a bunch of generators, then a group element can be written like this, where their summation over the repeated index A is implied. And let's say, okay, let's call this alpha. And this has to be a group element, so it also should be expressible in this form. But this demand that two composition of two group elements, each of which can be written down as a exponential of generators, is also going to be an exponential of generators. This is what tells you that ultimately there has to be an algebraic structure here, which essentially can be figured out this way. Suppose I gamma c xc is after all log of this quantity, right? But what we can do is write it like this. The reason why we are writing it like this is simply because this is going to give me a way of expanding for small values of alpha and beta, right? This is when alpha and beta are small, then in a sense this is going to be close to the identity. If it's going to be close to the identity, this you take away the identity from it, whatever you have here is going to be small, right? So this thing is going to be small, and because it's small and it's added to identity, you can just use Taylor expansion for log of I plus some variable. Okay, so let's call this something. I'm just following Georgi here. Georgi is not very rigorous as far as various steps go, and some of the well, unfortunately, Georgi would have been a wonderful book for physicists to read, and it is if you want just the physics out of it. The problem is there are many places in Georgia where the steps are sort of non-rigorous. I would say none of the results are wrong. The only problem is sometimes Georgia uses results which have not been proven, as if they have already been proven, and proves the result using that. Sometimes even, uh, even lapses into circular arguments where some result is proven later which actually was already assumed in a
Sir,
previous derivation.
sir,
Yeah.
your presentation stopped.
I don't know why that's happening today all the time. Okay, so this is what we were trying to do. Write e to the I gamma c x c as log of identity plus k, where k is just this quantity, which really is e to the exponential of I gamma c x c minus I. Okay, and what we want to do is basically check out this thing to the second order in the small if alpha and beta are small, then we are going to look at this up to second order. Up to first order, you don't get anything interesting. But if you go up to second order, it's going to be pretty interesting. So K, of course, is this quantity, which is if you just stopped at the first order, let's just see what you get. Then you get identity plus I beta b x b plus nothing else. I'm leaving a gap here because I will put in a second order term soon. So if you just use this much, what you're going to get is simply, you multiply them together, you get I alpha A plus beta A xa, right? And then I gamma C xc, which is log of I plus k, is simply going to be k minus, of course, there is minus k square by 2 and so on, but yeah.
Sir, shouldn't that be alpha xa beta b xb?
Right, but should it be? Isn't beta A xa is the same as beta B xb, right?
But xa and xb are different generators, right?
No, wait a minute. Beta A xa, what does it mean? It means beta 1 x1 plus beta 2 x2 plus beta 3 x3, sum of all of them.
Oh, sorry.
It's a summation. Yeah, yeah. So yeah, I guess I should have stressed once again that a summation convention is at work here. The reason why I wrote A and B separately is because when you multiply them together, which we are not doing at this stage because we are only looking at first order terms, but if we looked at second order terms and we were to multiply them together, then of course this A and this B would have to be different dummy indices. I hope everybody knows that, right?
Yes.
Okay. So up to first order, this is where you have to stop. If you're only calculating up to first order, you can't go beyond this because you have already, the minus k square by 2 will have second order terms in alpha and beta, but you've already ignored them here, right? So all you will get is I gamma c is alpha a, sorry, gamma c xc. So if you want to compare them together, you have to make them coefficients of same x. So gamma a xa. Again, this is a dummy. This is dummy. So sorry. What you end up with is simply gamma a is alpha a plus beta a. Sorry, not beta b. Well, this is sort of okay. When the parameters are infinitesimally small, they add. At least to first order in them, they add. But this doesn't tell me anything else about the nature of the generators. Okay, to see what you are saying about the nature of the generators, let's continue the second order. Now, this is the advantage that you have because of the Lie group structure. Let me stress this once again. This only tells me what happens to the group elements when you're close to the identity, right? That basically you were saying that when the element is close to the identity, when the parameters were zero, then the group element was the identity. Or this really is not the group element, there is a matrix representative of the group element. And then when the parameter was a small infinitesimal value or very small value, you would have a first order correction. But as I said before, the first order correction is just a first order correction, the first derivatives. In general, if you know the first derivatives of a function at a point, you have no clue about the second or higher derivatives. But because of the one parameter subgroup structure which T groups have, you can always choose parameters in such a way that you're going to get exponentials, which means not only do you know the first order term, you also know the second order term. In fact, you know all order terms, right? Alpha a xa whole square plus higher order terms. Similarly, I square by 2 factorial. Okay. So if you want second order terms, you have to keep both expressions up to second order. Then again, if you did the same calculation, you will of course get this to the first order. But what you will also get are these. You get minus half alpha a xa whole square. That is essentially this times the identity. You will also get minus half beta b xb whole square. Of course, as long as they're separate, I can keep on calling them alpha axa beta b xb or alpha axa beta axa. It doesn't matter. What is important is that you also have a cross term, which is a product of these two, and that works out to be minus just the product of these two. So alpha a beta b xa x plus higher order terms, right? So that's what k is. But if you're going to calculate up to quadratic order, then you really should use the quadratic order of K also here. Okay. So K is this. And now you see I gamma C XC works out to be this comes from K, whatever you have written down. I can just write down K once again. Hopefully I should be able to select and copy. Let's see whether I can do that. Okay, so this is what you have from K, but then you also have K square. So where will you get K square from? Or what will you get from K square? K square, of course, will have terms which K is just this. So in K square, these terms will also contribute, but these will all contribute to higher orders, right? To more than quadratic order. The quadratic order will essentially come from, from the square of this term, right? So basically, what I have is I alpha A XA plus I beta B XB to first order, and you square that, what you're going to get is there's a minus half in front, let's remember that. Okay, you don't get plus, you get a minus. Sorry. Okay, is this color visible at all? The light green?
Yes, sir.
Okay, that's fine. So this minus alpha XA whole square minus beta B XB whole square from the square of the next term. So as you can see, these terms merely cancel each other out, right? But you also have one more term which comes from the square, and what do you get from the square? You get minus alpha A beta B. But you don't get XA XB, you get XA or twice XA XB. What you get is XA XB plus XB XA. Right? So when you square alpha A XA plus beta B XB, you get two terms which cancel with the terms you already have. Okay. Now you are going to end up with this term which you already had. Maybe I will just switch to. So that's what I gamma A XA is equal to this plus an additional bit. An additional bit, these two just don't cancel each other out. So what you get is half alpha A beta B, okay, XB XA minus XA XB. Right? So you have the commutator of XA and XB sitting here. So what does this tell you? This is up to quadratic order. This is exact. Of course, there are higher order corrections. But what this tells you is that if you have to have this form, that is, you know that whatever you have here has to be a linear combination of the x's. This term is already a linear combination of the x's. What this tells you is that this quantity, which apart from a sign is just XAXB commutator, must be a linear combination of the x's in order that this formula makes sense. So this is where the commutator or the importance of the commutator in the for the generators comes in. This has to be a linear combination of the generators, and basically because we have been choosing these to be Hermitian generators and their commutator is going to be anti-Hermitian, you're throwing in an I. This again is a problem, is basically the mathesis problem. Mathematicians happily live without the I. The I here ensures that these quantities end up being real. Okay. So these number, okay, if ABC, all that you are saying is if you take the commutator of two generators, the result has to be a generator. Because unless that happened, you will not be able to combine two group elements with the I alpha, I A alpha, alpha A X A with the I beta B X B and get another group element. Okay? So this is why commutators are important. Yeah? And this is why what you're insisting on is when you take the commutator of two group elements, or two generators, sorry, not group elements, you end up with a linear combination of the generators. So some coefficient sitting here, and the question of course will depend on A, B, and which one this is, the coefficient of C, and this is sum over C, of course. And all these real numbers F, A, B, C are what they essentially tell you what the structure of the Lie algebra is all about. Okay. Now, what turns out, and this is something which I'm not going to prove because I don't have the time again, but there's something that easily read up anywhere. There's this BCH formula. Okay, just give me a moment. Oh. You have this BCH formula, Baker-Campbell-Hausdorff formula, which essentially tells you how to combine exponentials. Oh, that. Just hold on, give me time. Okay, so wait a minute. This is not what you're supposed to see. Okay, so what the BCH formula actually tells you is this: that when you multiply two groups to things like this, you don't get into the A plus B, but what you get is an infinite series. And what the terms which are sitting in the infinite series are basically things like commutators of A and B, then double commutators, and B comma A comma B, and higher order commutators, triple commutators, quadruple commutators, and so on. In general, it's an infinite series. Of course, you may have, I'm pretty sure all of you have seen a simpler version of the BCH result, which is the thing which happens when A comma B, the commutator, commutes with, if this commutes with A and B both, which is a simple case which happens, for example, with A dagger, and so on, then all these higher order multiple commutators vanish and you end up with a simple formula, relatively simple formula for the product of two exponentials. But in general, even if this were not to occur, that is, if the commutator of A and B did not commute with all of them, what you will get is higher and higher order commutators like these. So if the system is closed under commutation, that's all you really need. These structure constants essentially keep on occurring over and over again in these terms. So in principle, if you just know the structure constants, if you know how XA, XB commute to give a new combination of generators, that's all you really need to figure out the group composition law. So what I mean is if you have two group elements, alpha XA, the I alpha BXB or beta BXB, and you combine them together, we have already seen what gamma C will be or to first order. We have also seen what it will be to second order. We have not seen it, but you can easily deduce that from here. You just take this expression, plug that back here, and compare two sides, you can get the second order expansion for gamma, for the gamma. The important thing is, because the Baker-Campbell-Hausdorff theorem says this product can be continued to higher and higher multiple commutators, then just by evaluating these multiple commutators in terms of these, if you know the structure constants, you essentially end up knowing the group composition law. You should be able to find out when you compose parameters two group elements with parameters alpha and beta, what is the parameter gamma going to be? In general, the composition rule may turn out to be extremely complex, but at the heart, there is this very simple thing that if you know the structure constants, you know everything. Is this okay? Any questions about this so far? More importantly, I'm still here, right?
Yes, sir.
Okay. So, again, something not. Okay, so what we have done is we have established this algebra group theory connection, the Lie group and Lie algebra connection. Well, with the catch that I have not really proven the BCH theorem for you, but the BCH theorem is pretty straightforward. You can find the the proof is rather lengthy, but there's no very uh, complicated issues here. So you will find the proof in many textbooks. There are multiple proofs, and these proofs can be sort of easily understood if you know, basically if you know Becker-Hausdorff of lemma, which I'm pretty sure all of you know. Using the Becker-Hausdorff of lemma, you can actually prove the Becker-Campbell-Hausdorff theorem rather well. Rather easy. Okay, the ease is of course relative. But because of these two, but before you even get there, remember the important thing was here, that if you calculated this thing to second order, you found that unless the generator's commutator gave you a linear combination of the generators themselves, the algebra, the group wouldn't have closed and wouldn't have been a group. Okay, fine. So that's one part of it. Now, I don't have the time to go through the rest of it anyway, but I will just give you one very important result which you all should really know. Now, the important thing is, okay, before we go there, I wrote things like this. Georgi doesn't do that. Georgi starts with this. That is, essentially says that there is no real difference between the upper and the lower indices. Actually, there is a difference, but it so turns out that for Lie algebras, you can choose your basis in such a way that the difference disappears. So one first question would be, what happens when you change your basis? And that's actually quite an interesting question. So what happens when you go from xa to x prime a, which is perhaps some linear combination of the original x's? Okay. You should be able to figure it out yourself, but you will find that in this case, you would start with xa comma xb. Okay, let me just use pq here, xp, just so that we keep the indices well separated. I'm going to use indices on the middle of the alphabet here. So this is not correct. This is the changed commutator x prime a comma x prime b is going to be this, which of course is LAP, LBQ, XP, XQ. Are XR. But this is not enough to tell you what the new or so you're writing x prime a, x prime b, right? If you could expand that in terms of x prime c, you will get f prime abc. Yeah. But you have XR sitting here. So what you really need to do right? So f of ABC, the new, f prime ABC, the new f ABC is actually related to f PQR in a sort of slightly complicated manner. There are two L factors, one L inverse factor. Basically, it's the way in which 2-1 tensors transform, sort of like that. Okay. So this is the transformation rule, but in most cases, the kind of transformations we do are so simple that we don't have to really go through the entire transformation rule. We can easily calculate, or the general transformation rule, we can easily calculate what the transformation is going to be. And so what is important is the same Lie algebra may end up presenting itself in very, very different versions because of the way these coefficients are sort of connected to each other. And it turns out that very often you can simplify the presentation a lot compared to what it started out with, just by choosing the transformation appropriately. How that is done in general is, of course, and then you can always do it in general is important. Again, okay, this is something I would refer you to Georgia's book. Georgia gives you another simple way of seeing or rewriting this transformation in terms of the way in which a matrix transforms, and from that tries to show you how you can simplify the structure constants a lot. In particular, why you should be able to write down the structure constants with lower indices always, so that the upper index behaving differently doesn't really show up. And more importantly, if you look at the original definition, there is a symmetry property of the coefficients, right? What are the symmetry properties? If you interchange P and Q, what would happen to FPQR? Look, this was the definition. XAXB commutator is IFAB CXC.
Minus. That will be
So
minus.
it is going to be antisymmetric definitely in the first two indices, right? Okay. But will it be antisymmetric in the last index? Or of course can't be antisymmetric in one index, but will it be antisymmetric on all indices? Yes. Of course, if you remember our examples, the ones we know, this one, of course, is one of the most famous examples of Lie algebras we all know and have worked with. This is definitely antisymmetric in the first two indices, but it's actually antisymmetric in all three indices, right? The epsilon parameter, which is the structure constant for the Lie algebra SU2. But it turns out that you can actually do a coordinate transformation, and that is a basis transformation really. Instead of using the x1, x2, x3, you could use a new basis x1, x prime 1, x prime 2, x prime 3, and you can always guarantee something can show from this transformation law, but you can always guarantee that you are going to get a new bunch of structure constants which are antisymmetric in all three indices. Okay. Okay, I think I got lost somewhere. So I hope I'm back.
Yes,
Yes,
sir.
And how much did I lose?
10 seconds.
Okay, so not much. So what I was saying is, although the structure constant in general is only guaranteed to be antisymmetric in the first two indices, you can carry out a transformation of basis such that in this new basis is guaranteed to be antisymmetric in all three indices, and that's the one which we usually use. Okay, but of course not always, as you can see. You know all this, right? This is something which everybody knows. And this is not antisymmetric in all three indices. Here your three indices, 3, plus and minus, and you can easily check that this is not antisymmetric in all indices. Okay. So for example, f plus minus 3 is actually 2. You can easily see from here. And f 3 plus minus is how much? How much is f3 plus minus? Is something you can easily read off from here. Is how much?
-1.
No, it's not. These are okay. This is not first one. These are actually two. How much is f3 plus minus? You should be able to read off by looking at this as two separate. These are two separate commutation relations, right? I've just written them together.
0.
It's 0.
Yes.
J3 comma J plus, of course, doesn't have a J minus component, right? So, in fact, I shouldn't even write the 3 downstairs here. I should really be using my old notation, which really treats the 3 indices separately. The 2 indices downstairs, the thing is antisymmetric in, the other index is different. So, the 2 standard bases that we use for the SU2 algebra, for one, the structure constant is actually antisymmetric in all indices, but in general it will not be. That's the important thing. The other one which we commonly use is not antisymmetric in all 3. So that's one important point, because very often people fall into the trap of assuming structure constants are always going to be antisymmetric in all indices, and that leads to a lot of mathematical problems. Now, I will quickly jump over to one very important result, which I will not be able to describe this in full, but I'm pretty sure one of you, the one who is talking about SU3, will have to talk about this in the context of oops, once again, I didn't want to intimidate you by showing you this. Anyway, so the Kata analysis of semi-simple Lie algebras is actually very important. In fact, this would have been one of our major topics if we had time. We don't, but what we want to show you is something like this. If you have a semi-simple Lie algebra, okay, what does a semi-simple Lie algebra mean? I need to at least define that much. For that, we need to first define what is an ideal of a Lie algebra. So, first of all, you have subalgebras. What are subalgebras? Given a Lie algebra, how would you define a subalgebra? It's of course a subspace. Remember, a Lie algebra is a vector space, right? Very often we confuse the generators with the Lie algebra, but the generators really are basis of the vector space. The Lie algebra is a vector space on which the Lie product, in this case the commutator, has been defined and is closed under the Lie product. The basis vectors only help us to study this simply. Okay. So if you have a vector subspace, which is closed under the commutator bracket, then you call that as subalgebra. So you start with a vector space on which you have a commutator bracket. The whole space is closed under that. That's your Lie algebra. I hope I'm still there. Yeah, I'm still there. Okay. And if you have a subspace which is closed in its own right, then you have a subalgebra. Now, an ideal is a special kind of subalgebra.
Sir,
Yeah.
in the example you were talking about JZ, J plus minus basis. So
Yeah.
JZ and J plus, would they form a subalgebra? JZ and J plus, that's all.
JZ and J plus would form a
Subalgebra, because its commutator is also J plus.
right. JZ J plus is a subalgebra. Perfect. That's J plus. So if you took only linear combination of Jz with J plus, and of course that's not the only D algebra, only commutator, there are, but the other two are trivial, right? Jz is 0 and J plus is 0. So if you took this linear combination, what you will end up with is a Lie algebra which is closed in itself, right? It will not be a real subalgebra, by the way. That's only the only reason why we are diffident about calling it a subalgebra so much is that you have to make complex combinations of J plus and of Jx and Jy to get to J plus. So that's really related to something called a complex extension of a Lie algebra. That's slightly technical, although frankly we all know this, right? Whenever we are talking of eigenvectors of even a real matrix, it's not always guaranteed that the eigenvector of a real matrix, like say the rotation matrix. How many eigenvectors does a rotation 3x3 rotation matrix have? And how many eigenvalues?
It has one real eigenvalue and two complex.
What is the real eigenvalue?
I mean, identity. It's across that rotation axis.
Yeah, so we just look at the geometry, it's obvious that there's only one vector in the real 3D space which stays, or not one vector, but one direction, one ray in the 3D space which stays invariant under the rotation, which is the axis itself. So any vector along the axis, which of course gives you a one-dimensional subspace, that's an eigenspace. And the eigenvalue, of course, is 1. But that's the only possible real vector. So if you want to find all eigenvectors of this, you'll have to go beyond that. Okay, you have to go beyond real numbers, you have to go to complex numbers. In fact, the two complex eigenvalues are e to the I theta and e to the minus I theta. Okay. And where theta is the angle of rotation. Now, there is a reason why I brought up complex eigenvalues and eigenvalues and eigenvectors in particular. So we'll quickly go to that. Now the ideal essentially is to a Lie algebra what normal subgroups are to groups. Remember, if you had a normal subgroup, what would happen is you would took n, the entire normal subgroup, that is every element of the normal subgroup, hit with a G on the left, G inverse on the right. What you are going to get is again n back. Okay. Now, an ideal is a scenario like this. An ideal, say, let's call this ideal is spanned by elements H, let's say. Okay, take any element from the ideal H, take a commutator of that with any element from the full basis, let's call that X, full space, let's call that X, or whatever, let's call that small g. Small g typically is, in this context, when you're talking about Lie groups and Lie algebras together, small letters stand for algebra elements. So if you take this commutator must belong to the entire Lie algebra, right? But if you have an ideal, so this I, okay, unfortunately this I can be confusing with the identity. But if the commutator of every element, this belongs to the ideal, this belongs to the entire group, algebra, L. If this belongs not to L in general, but only to the ideal, that is, the commutator of two ideal elements, of course, will be an ideal element. That's basically saying that the ideal is the subalgebra. But if you take the commutator of an ideal element with every element in the group, okay, and you end up with an ideal element, then what you have, then you end up with an element in the same subspace, then that subspace is an ideal. But can you see the connection between the ideal concept here and the concept of the normal subgroup? What is the normal subgroup? The basic idea is you take any group element G dash, okay, let's call that, okay, I'm now in a bit of a quandary because I'm using same kind of letters for both group and algebra elements. So I'm going to change that. These are group elements, right? So G dash belongs to N. This implies G dash G inverse is going to belong to N. Now, G dash G inverse, of course, is a group element, so it has to belong to G somewhere. But if your set from which or subset from which you have picked your G dash is a normal subgroup, the result is going to be in that same normal subgroup. It's not going to go out of that. So that's the special situation which makes a normal subgroup a special kind of subgroup of G. Here, okay, let's not use small g and small h. Let's use some other letters. Let's use x, y, z. So x is an arbitrary group element. Let's say I is an ideal element. Now, this being a commutator of two group elements has to belong to two algebra elements has to belong to the algebra. But if it actually ends up belonging not to the entire algebra but just to the subalgebra I, then what you have is that this Lie subalgebra is an ideal. Now, how are these two connected? Can you tell me that? And the hint is something you already have studied in quantum mechanics. Remember, the group elements are exponentials, right, of generators. So what you have here is some exponential of all generators times G prime some exponential of all generators with a minus sign. So if you have something like this, and this also is of course exponential of just the ideal generators. But when you have something like this, what would you immediately use? In quantum mechanics, if you had an expression like e to the power a, b, e to the minus a, what's the obvious thing you would use? Yes? You all know this, right? The expression for this, which is?
It has commutators of A, B.
Yeah, plus 1 by 2 factorial a comma b and so on. This is the Baker-Hausdorff lemma, right? The important thing is, in the case of a normal subgroup, what we are demanding is that the result be in the normal subgroup. So if you take a Lie group whose elements are exponentials of combinations of generators, and now you focus on this element G prime being from the normal subgroup of a Lie group, then when you carry out this calculation for an arbitrary group element here, which means any generator will sit here, any generator for the entire group, but here you have only generators from the normal subgroup. Then what happens? Because of the Baker-Hausdorff lemma, the entire calculation hinges on taking commutators of whatever generators are sitting here and whatever generators are sitting here, right? And then, if it so happens that the generators sitting here have commutators with every group element which belongs to this same set, then you can say that this resulting thing will only involve generators belonging to the normal subgroup, nothing else. So an ideal essentially is a Lie algebra which corresponds to the normal subgroup of a group. So in other words, if you take the entire group, it has a bunch of generators. A subgroup will have its own bunch of generators, of course. But if the subgroup is a normal subgroup, then the corresponding bunch of generators will have to be an ideal of the entire Lie algebra, which means the commutators will only belong to that subspace and will not go outside that. Is that okay? Does that make sense, or have I made this completely confusing?
No, it makes sense, sir.
Okay. And this is where the notion of simple and semi-simple comes in. Just like if you have normal subgroups of a bigger group, you may think of trying to write down that group as a direct product of the normal subgroups, or sometimes you may have to use the semi-direct product notion if you don't have enough normal subgroups and so on. In the very same manner, you can think of building up an Lie algebra using its ideals. Okay? And things which cannot be broken up into ideals any further. So a group would be called a simple group if it did not have any non-trivial normal subgroup, right? Remember, that's what we talked about before. That means you cannot really write that as direct product of smaller groups. And once you have these simple groups, you can use them to build up bigger groups. This very same thing can happen for algebras. If a Lie algebra does not have a non-trivial ideal, why do I say non-trivial ideal? Because there are two ideals which are always there. One is just take the zero vector. That is, remember the Lie algebra is a vector space. There's a null vector in that vector space, and the commutator of that null vector with every group element is the null vector back again, which means, of course, that's a close that the null vector alone gives you a vector space which of course corresponds to only the identity in the group element. If you take the null vector, take any linear combination of that and exponentiate that, you're going to get the identity in the group. So in the group, whatever is the identity that corresponds to the null vector in the algebra, and the null vector alone is an ideal, and the entire Lie algebra, of course, is an ideal. So if you leave these two out, if there are no, these are the trivial ideals which every Lie algebra has. You leave these two out, then whatever you have, whatever other ideal you have, a non-trivial ideal, uh, these are the things you're going to look for. And if a Lie algebra does not have any non-trivial ideals, you call it a simple Lie algebra. Okay? And it turns out that if a non-trivial ideal exists, but it's at least non-abelian, even then the theory goes on, can be sort of, theory of simple Lie algebras can be extended in a way to even sort of extend them to those cases as well, which is why you have this very important classification of a semi-simple Lie algebra, which has no non-trivial abelian ideals. Not having an ideal at all, not having a non-trivial ideal at all, makes a group simple. A group may not be simple because it has a non-trivial ideal, but if that non-trivial ideal happens to be non-abelian, then at least it's semi-simple. Okay. If it is a non-trivial abelian ideal, then that actually makes life somewhat complicated. Okay. There's a full-fledged theory which tells you how to build up representations for complicated Lie algebras from its ideals and the semi-simple bits which make it up. We are not in a position to go through the whole thing, but thankfully, most of the important Lie algebras in physics, most of them, not all of them, happen to be semi-simple Lie algebras. So the theory of semi-simple Lie algebras, which is rather simple, is what most physicists have to focus on. Okay? And in semi-simple Lie algebras, what you have, this is the Kata analysis, and I'm not in a position to complete this for you, but I will just indicate why the things work the way they do. You essentially find out that there is a bunch of generators after you do sufficient amount of change of basis, you will find a bunch of generators which commute entirely among themselves. Okay. And then, so they give rise to an abelian algebra, subalgebra. If you just take their combinations and exponential, they only commute among themselves. That's an abelian subalgebra. And the exponentials give rise to group elements which commute among themselves. An abelian subgroup. But in addition, you will have further generators beyond that. Okay. Now, okay, let me see what the easiest way to put this. Of course, you know examples, right? You know the J3. So we had J1, J2, J3 for SU2. None of them commute with each other. So if you want to find the Kata subalgebra, what will you have to do? Kata subalgebra is some generators which commute among themselves. So what's the Kata subalgebra for SU2? Yes? Some you have to find a bunch of generators which commute among themselves. So which one is it? That's easy. In fact, you already know this. You may not know the name, but you definitely know this. Yes?
J3.
Well, actually, could be any one of them. Or any one of them, or any linear combination of them for that matter. The one which we usually use is J3. Well, J3 is not the subalgebra. J3 and all its the one-dimensional subspace spanned by J3. That's the subalgebra. That's the Kata subalgebra. Okay? J3 is really the generator or the basis for that subalgebra. We use J3, you could have used J1, you could have used J2, you could have used any linear combination whatsoever. But basically, this is the Lie subalgebra that you are going to use. That's the one which we use conventionally. But then something special happens. The other two Lie algebra elements can be always recombined in such a way, at least we did this, right? We wrote it like this. In other words, J3's commutator with J plus minus turns out to be a multiple of J plus minus, right? For J plus, the multiple is 1. For J minus, the multiple is minus 1. And you all know that this is very, very important, right? The whole point that we have of being able to build up angular momentum eigenstates by using ladder operators, these J plus and J minus, why are they ladder operators? They are ladder operators simply because of this commutation relation, right? That because J3 comma J plus, the precise form actually doesn't matter so much. What is important is this, right? Well, lambda is some number. In this case, lambda happens to be plus 1. Okay. You all would agree with me there, right? Because of the fact that there is this simple commutation relation that you have, then any eigenstate you have of J3, you can actually apply J plus on that and get an eigenstate of J3 again with a different, in fact, with an eigenvalue which is bigger by lambda. In this case, you get bigger by plus 1, right?
Yes,
So
sir.
the question I have for you is, if you look at this equation, what kind of other mathematical equation does this remind you of? What kind of equation that you use in mathematics quite often looks somewhat like this? At least the right answer definitely looks like this. By the way, I deliberately chose the letter lambda for a reason, for this reason, to make it look more like this.
Eigenvalue.
Yeah, it looks like eigenvalue, but except that when you have an eigenvalue, what you have is, what you would have expected is some operator sitting here. And if you had that, then you would say neatly that this is an eigenvalue equation, right? Is that okay? But an operator which is acting on J plus to produce lambda times J plus, then it would have been an eigenvalue equation. This is not really an operator acting on J plus. This is a vector. By the way, remember J plus is a vector here. J plus is no longer an operator as long as this part of the story is concerned. In this part of the story, J1, J2, J3 are just elements of a vector space. They have a Lie bracket which gives you something in that vector space. And these are just vector space elements. Of course, there are states which these J3, J plus, J1, J2 act upon. And when you talk of those states, then these become operators. But within themselves, they are just vectors in a vector space. And so there is no operator in this equation, but there can be. And that is the important thing which I will really talk about. That's a very important result, which is for every Lie algebra element A, you can have a corresponding operator add A. Okay. So, in a sense, because we think of A, B, C, the Lie algebra elements themselves as operators acting on some space, you might be tempted to call this add A a super operator, an operator which acts on operators. But if you realize operators form a vector space, this operator is a vector space which is an operator which acts on that vector space. So there's a correspondence between A and add A, and how do you define add A? That's very simple. you would have to tell me what add A does to every vector in the space, right? The vector in the space is another operator here, or another Lie algebra generator for us. And by definition, add A acting on B is this. Okay. You should easily be able to check that this is a linear operator, right? Is that okay with everybody? That is, add A is a linear operator, this one. Is that okay with everybody?
Yes.
Okay. Now, why is add A so interesting? It's interesting because of this result. Suppose I took add A, add B, and acted upon some Lie algebra element C. What will this be? It will be A commutator with add BC, and add BC is of course B comma C. What's add B, add A? That's actually B comma A comma C. Now, since these are operators acting on C, you can easily define the commutator of these two operators by saying that add A, add B, what is the commutator? By definition, it's add A, add B minus add B, add A, right? So add A commutator, add B acting on C is simply the difference of these two terms. But whenever you have things like this, the obvious choice would be to try to put them in cyclic order so that you can make use of our Jacobi identity. So this first term is A comma B comma C plus, okay, if you want to put them in cyclic order, B comma C comma A, right? But then you know that if you added C comma A comma B to this three, these two, you're going to get 0. So, but now you can flip the order over. A comma B comes first, then C, and that's add. So what that means here, and this is very, very important for us, that this map, which maps the operator A to corresponding superoperator add A, this map is actually Lie algebra homomorphism in the sense that add A commutator with add B, whether you first do the map and then take the commutator, or you first take the commutator, then do the map, you get the same result. Okay. The commutator of the adjoint operators, okay, this is also called the adjoint operator, but please don't confuse this with the other adjoints that is often used in different parts of the language. Add A commutator add B is add A commutator B. Now, why is that so important? The important thing is if you go back to these results, this really is add J3 acting on J plus is J plus. Add J3 acting on J minus is minus J minus. So what we are saying simply is add J3 is an operator. It gets to act on the space of J3, J1, J2, right? And we know what the rules are. Add J3 acting on J1 gives you J3 comma J1 is IJ2. Add J3 acting on J2 is minus IJ1. Add J3 acting on J3, of course, is 0. So you already have one eigenvector of add J3 staring at you in the face, because 0 is, of course, 0 times J3, right? So that's one eigenvector of the operator add J3 gone. But J1 and J2 are not eigenvectors of add J3. As you can see, acting on J1 by add J3 actually doesn't give you J1, it gives you IJ2. But now comes the question that J1, J2, the space spanned by J1, J2 is closed under add J3, right? You get only combinations of J1, J2 again, which means you should be able to find eigenvectors of add J3 in that space. So instead of looking at this as some funny way of suddenly finding out a ladder operator, why don't you just try to think of this as a eigenvalue equation? That is, you have two basis vectors in your space J1, J2, which acted upon by this operator gives you these results. Can you find out linear combinations of J1, J2 which will give me eigenvectors of J3? The answer is yes. And you already know what the combinations are and what the results are. What you get is at J3 acting on J plus is plus J plus, and at J3 acting on J minus is minus J minus. So J plus and J minus are just two eigenvectors of the operator at J3 corresponding to these two eigenvalues, plus 1 and minus 1. Okay? Now, why is this important in general? This is, of course, just if you had only SU2 to talk about, then there's just another way of looking at things. It's really not that great. It's not going to give you any extra insight over what you already know. You already know how to handle the SU2 representations. This is not going to tell you much more about it. It's just the same thing. Okay? However, and this is what is very important here, this is if you are talking about general Lie algebra which has a Kata subalgebra and other generators. Now notice that if you look at the adjoint operators corresponding to these Kata generators, what can you say about them? There are of course operators which are going to act on spaces, right? But what can you say about these particular operators? What's special about these particular operators?
They commute.
Yeah, these operators commute because add h1 comma add h2 is add h1 comma h2, and h1 comma h2 is 0, and it's easy to see that this is going to be 0. Okay. So now this is the important thing. Now we have operators add h1, add h2, add h3, and they commute with each other. So because you have if you have a bunch of commuting operators, what can you say about their eigenvalues and eigenvectors? More importantly about their eigenvectors.
Simultaneous eigenvectors.
Well, that's a bit too general. What you can say really is you can find simultaneous eigenvectors, right? Rather than saying all, when you just say simultaneous eigenvectors, it seems to imply that all eigenvectors are simultaneous eigenvectors. That, of course, is not the case. But in principle, you can always find eigenvectors E alpha, where alpha is nothing but the bunch of eigenvalues. Now that you have, say, R Kata generators, let's say, the R commuting operators, each one of them will have an eigenvalue. So alpha 1, alpha 2, alpha 3, alpha R, these will be the eigenvalues characterizing this eigenvector. And add hi acting on E alpha will give you alpha I E alpha for all of them. So the all important thing here is because the adjoint maps commute, they are simultaneously diagonalizable. And if you diagonalize them simultaneously, what you end up with are special eigenvectors, which are not Kata generators, but which essentially have this property that they are simultaneous eigenvectors of all the HIs. Or if you just go back to the commutator language, you have this. And what this says is that the operator E alpha acting on an eigenstate of the HIs are going to, by the way, HIs commuting among themselves means if you look at any representation of the Lie algebra, HI will be given by matrices which commute among themselves. And if they commute among themselves, or operators which commute among themselves, and if the operators commute among themselves, then they will have simultaneous eigenstates in that particular space. And what the E alphas will do is they will change the eigenvalues for each one of these. It's going to change the eigenvalue of H1 by alpha 1, H2 by alpha 2, H3 by alpha 3, and so on. So basically, what is happening is just like you had ladder operators in SU2, for any semi-simple Lie algebra where you can break up the thing into a bunch of Kata subalgebra generators and other generators, you can always diagonalize the other generators in such a way that you get this kind of relation. And that means this is for a specific case where you're using the generators, but now you can think of this way, that if you think of these operators acting on some vector space, then HIs will give you commuting operators, so they will have simultaneous eigenvalues, and the E operators will act as shift operators on them. They will just shift the eigenvalues by the vectors alpha. So alpha, alpha 1, alpha 2, alpha r is an r dimensional vector, and things are going to shift in that space. Okay? Is that okay? So that's where the geometric picture of Lie algebras come in. This fact that you can generalize this to whatever you did with SU2. Of course, with SU2 you had just one direction to go in. You could either go up or go down. J plus would move the things up, J minus would move the eigenvalues down. And if you had finite dimensional representations, of course, you would have to reach a state, special state where J plus would kill it, and here also J minus would kill it, right? For other semi-simple Lie algebras, what will happen is that you have a Kata subalgebra with multiple elements, not just one. So you have multiple directions you can move in. And that's what makes for the complexity. But the overall thing is really very simple, because in any given direction, it's basically like shifting the eigenvalues one at a time. Okay? Of course, this is not the end of the story, but this is basically where the story starts. And well, in particular, if you have a two-element Kata subalgebra, which is the case for SU3, you have this nice advantage that you can actually do things. Then the space of alphas, which are called roots, by the way, becomes two-dimensional. So you can draw everything in a two-dimensional picture. So all those pictures that you've seen of octets, decuplets, and so on, they're basically diagrams which essentially says what happens when you apply the E alphas and you're shifting in two dimensions, and that's why you end up with a two-dimensional picture. Okay? Of course, this doesn't end here. What is important is you can actually show something like this. Suppose you took the commutator of two such eigenvectors and took the commutator that with HI. How would you calculate this commutator? You would calculate this commutator simply by using Jacobi identity, so that this essentially becomes minus, okay, E alpha, comma, E beta, comma, HI. Now in each of these cases, I know that this is going to give a number beta I out. So this is going to give you the number beta I out of here, minus beta I out of here. So this is going to give you beta I, E alpha, comma, E beta. And what this is going to give you is alpha I, but then you'll get E beta, comma, E alpha. So another minus sign. So you get beta I plus alpha I, E beta, comma, E alpha. So basically what you see is E alpha, comma, E beta, the commutator, is essentially going to be E alpha plus beta times some constant. So these generators will have a closure among themselves in that sense. What's immediate from here is E alpha and E minus alpha. You took the two together. Okay, what will that correspond to? If you took commutator of E alpha, comma, E minus alpha, this of course is itself a commutator. If you took its commutator with HI or acted upon that by add HI, what will you get?
0.
You'll get 0. So what does it tell you about E alpha, comma, E minus alpha?
They commute.
No, they don't commute. The commutator with all the HIs is 0. So what does it tell you that? That doesn't mean they commute. They commute with all the HIs. They don't commute among themselves necessarily. Or other E's. An operator which commutes with all the HIs, what does it have to be?
Some linear combination of E alpha.
Of the?
E alphas.
No.
Of the
Wait,
HIs.
Some linear combination of the HIs, because HI, remember, is a maximal commuting algebra, subalgebra. Something which commutes with every one of the HIs has to be a member of the HIs, because if it were not, then you would have to add that to that set. Then it would be an additional thing that would only mean that you have not found your entire Kata subalgebra. This is one more element of the Kata subalgebra. You found out your Kata subalgebra properly, then this thing, because it commutes with all the HIs, has to be in the HIs themselves. So it has to be some combination of the HIs. And now I'm going to cheat a bit. The proof is simple, but I will just state the result. It happens to be not just any combination, happens to be this particular combination, alpha I HI. Okay? That is, the combination is with the eigenvalues themselves. And now, if you look at these three elements, alpha I, so E alpha, E minus alpha, which is alpha I HI, and E alpha and E minus alpha. This is again a calculation which I will let you do yourself. It's pretty straightforward. You can show that their this is closed under commutation. 3 generators, and if you take the commutator, of course, the commutator of these two is just this one. That's obvious. The commutator of this with this, for example, is just alpha I HI. It's commutator with E alpha. So what is that going to be? Alpha I, HI comma E alpha, and HI comma E alpha is alpha I. So that's basically alpha I, alpha I. So that's alpha E alpha. So alpha squared, in sense, alpha vector squared E alpha. Okay. Similarly with E minus alpha. So there are 3 generators which commute whose commutator is closed among themselves. So which Lie algebra do you know whose generators, which has 3 generators and have commutators which close among themselves? There are multiple, but you do definitely one which has 3 generators, right?
SU2.
SU2. And it so happens, it's pretty easy to show, that these, by a simple change of scaling, you can make these exactly the same as J1, as J3, J plus, J minus, the commutation relations. In other words, for each of the E alphas, you essentially have E alpha, E minus alpha, and alpha dot H, which gives rise to an SU2 subalgebra of the whole algebra. So ultimately, what happens is, if you know the SU2 subalgebra properly, and you know how SU2 acts on states, you essentially know how to build up the representation theory for any Lie algebra whatsoever. Okay. Now, so basically what you do is look for these eigenvectors, simultaneous eigenvectors of the add HIs. This corresponding eigenvalues will give you root vectors, that is alpha 1, alpha 2, alpha 3, alpha r. This is an r dimensional vector in a vector space. So these gives you a root vector, not one root vector. This gives you, of course, different root vectors for each one of the alphas and betas. And fine, so I'm just quickly telling you what results come out, and I expect that in SU3, when you talk about SU3, you should be able to connect all these things together. SU3 is easy because SU3 has only 2 Kata generators, so it's the entire thing is 2-dimensional. So all these pictures that you get, you can immediately write down in terms of this. And the one other important result which I'm going to just mention, not prove, but the proof is really rather simple, which is this. You cannot have any arbitrary relationship between the alphas and betas. There are very specific relationships which come from them. At least and that's pretty easy to figure out because, in general, for any finite dimensional representation, what you must have is that this E alpha, E minus alpha, basically what are they? They are like raising and lowering operators of the SU2, right? So if you keep on hitting with E alpha, you're going to go up in eigenvalue, or, well, not up, but at least you're going to add alpha every time, because there's more than one dimension. You may not be able to say which one is increasing, which one is decreasing, but you can go up in alpha, and E minus alpha makes you go down in alpha. So if you want a finite dimensional representation, what does it tell you?
Sir, could you repeat the question?
The E alpha, E minus alpha essentially work as raising operators, right? And lowering operators, or shifting operators to be more precise. You shouldn't really say raising or lowering. So if you keep on hitting with E alpha, you are going to go up, you are going to add alpha vector to the eigenvalues every time, right? And similarly with E minus alpha. But if you want a finite dimensional representation of your Lie algebra, what does this tell you about this process of hitting with E alpha and E minus alpha? Hmm? Yes?
E alpha and E minus alpha, like the commutator, should have finite eigenvalues.
More important, a finite number of eigen. That's not the point. The point is when you keep on going up, some stage E alpha acting on your state must give you 0. Right? Because if you kept on going this way, this is just like the ladder operators, right? If you keep on going forever, you're going to get infinitely many states. To get finitely many states, you have to stop somewhere. Okay? So there has to be an upper limit, there has to be a lower limit. And between them, the basically it's just the SU2 algebra again. You must given the SU, if you know the SU2 eigenvalue, which corresponds to the eigenvalue for this E alpha, E minus alpha after scaling, that has to be some multiple, some integer or half integer.
Sir, the presentation stopped.
Anyway, I don't have much time to continue today. So maybe we will take one more day later, somewhere. If you can give me some time later, we'll just talk about this in some more detail. But what I was actually telling you is simply this, and not this. What is this? Yeah. So what I was just trying to tell you is this. E alpha, E minus alpha is basically akin to J3. Not exactly, we have to rescale the thing. E alpha is like J plus, E minus alpha is like J minus, simply because that's what the commutation relations tell you. So if you keep on hitting with E alpha, you're going to keep on raising the eigenvalue. If you keep on hitting with E minus alpha, you're going to lower the eigenvalue. But each of these states that you get are new states, right? So you keep on getting more and more states. If you want a finite dimensional representation, number of individual states has to stop somewhere. What that means is there has to be an upper limit to how high you can go, a lower limit to how low you can go. And that essentially tells you that only certain values of alpha dot beta combinations exist. That is the angle between the vectors alpha beta, they have to obey certain very specific restrictions. Okay, I can't talk about this today. So can you give me one more day? Maybe just figure out one more day when I can talk about this. This is important. So I should be able to talk about this, preferably before your presentations, especially because there's an SU3 presentation. I would like the SU3 presentation to build upon these results.
So one more day in the sense before the next Tuesday?
Not necessarily. The next Tuesday we can't have it, right? Because can we have it next Tuesday? I have no problems, but can we have it next Tuesday? That is, are you all comfortable with sitting with that before your exam? If you are, I have no problems.